So the upper bound of this is fx minus fy is less than order of log n d of x and y. And the lower bound, unfortunately, it is just the expectation of f of x minus f of y. And this shows that we can still write articles and develop our theory. Is greater than order of dx and y. And we can replicate these d times. I will show you later how to do that, but I don't want to make it sophisticated. So let's say d is 1. We don't want to replicate it. But if you want to replicate it, I will show that it gets, with high probability, you can get a better distortion, lower distortion. And so by distortion, by replicating, so we are replicating. By replicating, I mean f is defined like this in the 2006 paper, if you look at that. So we have d of these constructions. So it's a vector that each of them is a construction that I will show you. And so ft of x is one of these psi I of t of x. That in the paper, psi I is defined by sigma I of t. So it's nothing new. Phi I of x. Instead of phi I of x, we can write pcp of pc and eta minus 1 of x. P and I. And d of x and x excluding pi of x. But let's see what does it mean. So if t is 1, so we say that, okay, we don't want to replicate, just 1 is enough. 1t is enough. It means that we want to cover our space with some big circles. This is the biggest scale that you can. So this is I equal to 3 because it is the biggest scale, corresponds to delta 3. I mean the radius, the diameter is delta 3. And you can also partition it with, partition this X space, this metric space, with some medium size balls. So these clusters are medium sized relative to the first one. So this is I equal to 2. And the extreme case could be your scale is too small. It means that in order to cover those points, you want to cover those points by some circle, by some balls. In order to cover them, you need to, this is the finest topology. So you need several of these balls. But the diameter delta 1 is so small. Here delta 2 is a medium diameter. Here the diameter delta 1 is so small. So t equal to 1 generates the three partitions, and each partition, the three partitions. And so t is equal to 1 makes induced graph by only one ball. So we have something and we induce it. For example, in the paper of Arnold, he created an induced graph by removing a shortest path. Here, for example, I like, for example, Abraham in general, in his theory, he has a ball. And removing that ball creates some partitions. So this is just for t equal to 1. But for t equal to 2, we can have another thing. So, for example, in shortest path decomposition, if you have seen my lecture, we divide it by some shortest path, and we have more partitions. And we have, of course, we have different scales as well for each of them. For t equal to 3, we make induced graph by more balls, so it becomes much more smaller, you know? It's like fractal. It goes to 0. So the scale goes to 0, from very, very high scale to very, very low scale. It's like fractal geometry. So that you get the intuition, geometric intuition, now you're ready to do some calculations again. But this time, we assume for simplicity and without loss of any generality, we can say that fixed t equal to 1. So from x, a map from x to LP, this L, little l, LP, but only having one coordinate. So this means that only one coordinate, because t is just 1. And so fi of x, recall that this is sigma I of pi of x. Sigma I is the Bernoulli times eta, that padding parameter that I was talking about, and times the x excluding pi of x. So for any x in x, of course, and any y in x, if they are in different clusters, then we can say that fi of x is less than eta I minus x, the x and y. Now our improvement with comparison to the previous embedding is that we have another term here. And if they are in the same cluster, it means that fi of x minus fi of y is less than eta I minus 1, the x and y. So in both cases, we get the same result. And the upper bound, as usual, is so simple. The upper bound is simple. Our difficulty, our challenge, our future research is related to lower bound because it leads to expectation, it leads to difficulty. You need to define a complex versions of padded decomposition. What is eta? How can you generalize that function? But the upper bound is so simple because you just need to write fi of x minus fi of y. I is greater than 0. This one is less than the x and y. Eta I minus 1 of x. And this is less than equal to, I prove that, log of cardinality of b of x and 4 delta I divided by ball of x and delta I over 4. And fortunately, this is less than order of log of n, d of xy. So good embedding, but this is the upper bound. So let's work on lower bound, which is much more sophisticated. And we should create new theories. Lower bound, so we take scale I such that delta I is dxy divided by 4. So it must be that if pi of x is not pi of y, it means they are in different clusters, then with probability 1 over 2, again we can say that f I of x is equal to eta y of x, d of x and x excluding pi of x greater than delta I. And this is not magic, because you just know that you have deliberately created a partition such that this is greater than delta I eta I of x with probability 1, with probability half, because you defined padded decomposition. So rearrange this, you get that. So it's not something special. So R, let's define R by the sum of these differences, fj of y. And of course, j not equal to y. So two cases happen. So either R is less than delta I over 2 with probability 1 over 8. You might say why? Okay, I say that with probability half, we have this relationship. If I of x is this. So this is 1 over 2. With probability half, I can say that sigma I of pi of x, this is Bernoulli, is 1. So this is 1. This is half. Because it is Bernoulli again, with probability half, I can say that pi of y is 0. So this is there. So if you multiply them, it becomes 1 over 8. That's why I wrote probability 1 over 8. So then we find that fi of x is greater than delta I, and fi of y is 0. And so the difference is now crystal clear that this one is less than delta I over 2, and this is omega of d of x and y. But we have another case as well, which is r greater than or equal to delta I over 2. In other words, r is this. So with probability 1 over 4, again we can say our Bernoulli picks 0, and our Bernoulli of pi of y is 0. And so fi of x is equal to fi of y. Because of this 0 term, it becomes 0. Both of them 0. So f of x minus f of y is greater than equal to delta I over 2, which is order of d of x and y. And so we got the lower bound, which is the expectation of f of x minus f of y is greater than d of x and y, which is pretty nice achievement. So you have seen the basic idea, and now you are ready to learn and read the 2006 paper. We are ready. Your mind is ready for that. Because in that paper, as I said, the decomposition looks very complicated, because they defined several variables. Of course, we need them. But if you watch my video, then now it's easier for you to understand what's going on and what is the big picture. So the embedding, D is just the sum of T f of t. Remember, f of t is from x to r plus. And psi I of x is sigma I of t, pi of x, phi of t, d of x and x, pi of x. And this guy phi is just, as I said several times, it is just the multiplication. And I just want to review the Lemma 3 because they define eta and delta uniformly padded. And it basically says that there exists a probability for hierarchical partition any uniform collection of functions, these functions, Kc, such that the collection of functions eta, these functions eta, defined below, I mean, they happen to satisfy this interesting relationship, is less than 2 to the 10 ln of n divided by b of cardinality of b of x and delta I plus 4. So if Kc is 1, then eta is... But now I want to show you other stuff that is interesting. So you are now ready to understand that paper completely. So let's prove a claim. That's claim 8. So for any x and y in x, psi I of x minus psi I of y phi I x d of dx and y. I've proved it again, but I want to repeat it. I've proved it before, but I want to repeat it. So if they are in the same cluster, the same trick. We use claim 7 that says if they are in the same clusters, then their phi is the same. So we say that using this one, we can say that phi I of y is equal to phi I of x. And then you just write the definition of psi I, which is equal to sigma I pi of x. Now phi I of t of x is the same, so we can factorizing it. So d of x and x excluding pi of x minus d of y and x excluding pi of x, because pi of x is the same as pi of y, and this is less than phi I of x d of x and y. But case 2 is that they are in the different clusters. So pi of x is not pi of y. X and y are in two different clusters. So in this way, it is easy to see that the distance between x and x excluding pi of x is less than d of x and y. So psi I of x minus psi I of y is less than psi I of x, and this is less than phi I of x dx y and y. So we proved it. But lemma 9 is the final thing that you need to do. It says that there exists a universal constant C1 greater than 0 such that ft of x minus ft of y is less than C1 ln of n d of x and y. So the proof is simple, because from claim 8 and lemma 3 we can say that the difference between size for x and y is less than phi I of x d of x and y, and this is itself is less than 2 to the 11 ln of n.